Well, friends, today I'm going to talk about general relativity. If you've seen my last couple of lectures, you'll know that, well, light is basically described in special relativity. General relativity is the extension of special relativity. I'm going to talk about it again in another lecture because it's far too big a concept to squish into one. So, general relativity. In special relativity, it describes objects with the special case of moving in straight lines. General relativity describes objects that aren't moving in straight lines. Now, Einstein's general relativity came to him with an inspiration that a falling person, that's my best impression of a falling person, in an elevator will not feel his own weight. Of course, he will still feel his own weight even if he's falling, just from the rush of air above him. But the point is, Einstein found out that if an object is falling and someone is inside of it, it means he won't feel much of his own weight. And if the elevator was accelerating in the opposite direction, that means the person would be squished down onto the floor. Now, Einstein, the other part of general relativity that he found out was that everything contains this permeating substance, not exactly a substance, called space-time. In Newton's theories, what he found out, or at least he thought he found out, was that there's something called an absolute space and an absolute time. Einstein destroyed that, saying that space and time are the same thing. Space-time. And this space-time, you can imagine it, if you've heard my other lectures, as an elastic fabric. Large objects make dents in this space-time, much like how if you push your hand into a pillow, it makes a dent in it. And I'll talk about that later, but these dents can spring back up and cause gravitational waves. However, just a more elaborate version of this dent. In 1919, Arthur Eddington, one of the only other people in the world at the time who understood general relativity, decided to make an expedition to test if it was correct or not. Basically, what Einstein's general relativity predicted is that the sun, because it dented space-time, it would cause space-time to warp around it, meaning that light, passing from stars that were behind the sun, would actually be warped by an angle of 0.85 degrees. That was actually an error. He later recorrected this to 1.7 degrees. And light would bend around the sun at an angle of 1.7 degrees. Therefore, the stars measured at daytime would be in slightly different positions than at nighttime. Now, of course, you can't measure the position of background stars during the daytime because they're all overwhelmed by the sun's light. But you can with a solar eclipse. And there just so happened to be a solar eclipse at 1919. That meant Arthur Eddington could measure the position of these stars during the solar eclipse and during nighttime. And what he found was that Albert Einstein was indeed correct, that it diffracted by that angle. Now, this alone wasn't enough to prove general relativity, but it was a major, major stepping stone, and it proved the existence of Einstein's space-time. I'm just going to talk about how other objects can affect this space-time. Now, you will probably catch on that the more mass or the more dense an object is, the more it curves space-time. You can imagine this pretty simply. Say if you were to put a light book on an elastic material. It bends down, yes, but put something like a bowling ball on it, much heavier, but just say that it has the same density as the book, it will make an even bigger dent in space-time. However, if you put a pin in this fabric, it will cause an even bigger dent because it's denser. Now, the epitome of this heaviness and denseness is a black hole. Black holes are formed by supernova explosions or gamma ray bursts. Basically, an incredible massive star, up to 100 times the mass of the sun, basically implodes. Stars are powered by nuclear fusion, the combining of hydrogen in their cores to form helium. In the later stages of their life, they form heavier and heavier elements as they run out of each one. When they run out of hydrogen, they start fusing helium. When they run out of helium, they fuse, and you get the idea. Eventually, they'll start to fuse an element to make iron. Now, when they fuse iron, they can't fuse iron to form another element because they're just not hot enough. So iron builds up in the star's core until it causes too much pressure on the star's core and gravity takes over. Now that there's so much weight in the star's core, gravity implodes the core and the outer layers of the star explode out into outer space. And the core, the remnants of the core, decays into two things, either a black hole or a neutron star. Both of these are very dense and dense space-time a lot. Talking about a neutron star, because it still retains a certain amount of the star's properties, such as it still allows light to escape, it doesn't dent space-time as much as a black hole. However, in a black hole's case, it's so dense and so heavy that our laws of physics begin to break down at that point. Now, you've probably heard the myth that nothing can escape a black hole. Well, it's a bit more complicated than that. You see, light can escape a black hole as long as it doesn't reach a point known as the event horizon. Things have an escape speed. The Earth, for example, in the outer orbits of Earth, the escape speed is about 11 kilometers per second. At the lower orbits of Earth, close to the ground, it's about 11 kilometers per second. However, in a black hole, the escape speed at its lower orbits, or in the event horizon, is more than the speed of light. Einstein, in general and special relativity, stated that nothing, and I mean nothing, can travel faster than light. Therefore, if you reach the event horizon, you'll never be able to escape. But if you somehow manage to reach slightly above the event horizon, you could still escape, but you would still have to travel at an enormous speed. And that's again because of the denting and curvature in space-time. Black holes warp and dent space-time so much that light itself can't escape. Now I'm going to talk about gravitational waves, the other point of space-time. Space-time, as you know, is like this elastic fabric, but it can also be thought of as water. When you drop a stone into a pond or a pool of water, ripples start coming out. However, if you take two objects and rapidly spin them around in the pond, they also generate out ripples. And this is what happened when two massive bodies, such as two neutron stars or two black holes, orbit around one another, causing ripples in the very fabric of space-time. Now, these are what we called gravitational waves. And a big news recently, a couple of years back actually, that LIGO managed to find out that these gravitational waves are true. Gravitational waves do exist, and you need very, very precise and fine instruments to measure them. I'll just go on to how they actually do that. LIGO itself is made up of several lasers. These lasers are incredibly, incredibly precise. That these gravitational waves will move them by a tiny fraction of a distance. Because gravitational waves, because they're from gravity, aren't actually very enormous. They're not the enormous planet-shaking things that you imagine when thinking of a gravitational wave. They're actually really tiny. Hell, millions of them are probably passing through us every minute. We don't know them. That's why this laser is so accurate and precise that it can measure these gravitational waves. It's kind of like saying that a basketball is bigger just because it has an extra bacterium on it. So this laser was just moved by a tiny fraction, and that's how they managed to figure out that a gravitational wave had just passed through it. Several telescopes and astronomy work later, they managed to find that it came from two neutron stars. And that's how they detected gravitational waves. Now I'll go over other laws and theories about space-time, and of course the relating wormholes and white holes of relativity in a later video. Thank you.